Welcome everyone! In this video we will present TRAINMAN-MAGOS, one of the Trinity use case demonstration series. TRAINMAN-MAGOS is a finger tracking based solution which uses a sensorized glove to gather hand movements and translates them into a tangible set of instructions and trajectories to fit a combination of a robot and a gripper. The motivation to develop this solution was due to the complexity of automating high dexterity operations. Despite the fact that automation of manufacturing process has evolved enormously in the last decades, many processes still remain nowadays being executed manually due to the necessary dexterity to perform them and the complexity to replicate them using an automation or robotic approach. This high dexterity need makes automation a complicated and time-consuming task, but being able to automate such kind of operations would increase productivity and flexibility of the production line. Therefore, two partners have developed the TRAINMAN-MAGOS solution, which transforms the gathered hand movements and positions from a skilled operator performing a high dexterity task into a tangible set of instructions to a robot and a gripper. The partners who have developed these solutions are Quantum Qualia and CITAC. Quantum Qualia is a deep technological startup in human-computer interface located in Athens, Greece. Quantum Qualia has a multidisciplinary team which has participated in many European projects, being its main product the MAGOS platform, which consists in a sensorized haptic glove which provides finger tracking with up to 22 degrees of freedom, as well as orientation and indoor localization, which makes it useful for many applications. On the other hand, CITAC is the Automotive Technology Center of Galicia, a research and development technological center located in Oporriño, Galicia, northwest of Spain. CITAC was created in 2002 and it's a private non-profit research and development technological center devoted to support the automotive industry in its research, development and innovation needs. Having more than 800 people working, it has also collaborated in more than 50 European projects. As we have previously said, both partners have developed TRAINMAN-MAGOS solution, which is based on the combination of a sensorized glove, a collaborative robot, a collaborative gripper, and information system. The sensorized glove used in this case was the MAGOS glove from Quantum Qualia. This glove provides finger tracking with up to 22 degrees of freedom, which means that the glove can track up to 22 independent movements of the fingers. This glove has also orientation and indoor localization, which is used to monitor the hands of a skilled operator on one of these complex manufacturing processes. Then, the collaborative robot using the collaborative gripper mirrors the movements recorded by the glove. And finally, the information system translates hand movements into robotic and gripper programs which transform the gathered hand movements and position into a tangible set of instructions to the robot and gripper. TRAINMAN-MAGOS can hence dramatically decrease the development time of robotic implementations in those extreme dexterity cases and the implementation time for deploying the robotic operation. On the other hand, it is also interesting as a new tool to register and exploit this kind of skill knowledge usually confined and inaccessible. Talking about the state of the art, when replicating a task traditionally performed using human hands in complex operations, it's not obvious how to create a robotic trajectory without collisions, without respecting cycle time, and without respecting quality requirements. In addition, in these cases, each point and angle must be carefully selected and programmed so that the operation to be performed could be carried out correctly without harming any person or any element where the task is executed. Additionally, if the robotic system needs a robotic gripper, the difficulty to develop the program increases because a robotic gripper is a high-technology device that imitates the behavior of a human hand with more or less similarity. And, as you can imagine, gripper's complexity is directly related with its cost. In this case, the simplest and less expensive option in the market was selected, which was the robotic Q-gripper, as a means to make the solution accessible to every potential user. On the other hand, it is very difficult to express, in a detailed manner, neural control-related expert behavior in words or as a set of instructions. So one alternative is the use of gestures monitoring system that can automatically gather this expert knowledge. In this category, we find sensorized gloves, which includes different types of sensors to collect this usually inaccessible data. One of the best examples is the MAGOS glove, which was the one used in this solution and whose patent is still pending. Nevertheless, it can collect up to 22 degrees of freedom finger tracking, and it has hand orientation, indoor localization, and haptic feedback, which means that the glove gives the sensation of touching something real when in fact it is not. So, what makes Magos glove unique is its level of accuracy, offering 250 times more accuracy than its competitors, as well as the highest degrees of freedom in the market. Continuing with information capture, when a system is used to collect movements from an expert, this data can be used almost directly to have a first draft trajectory and gripping steps. This draft trajectory must be refined afterwards by an expert robotic technician, either using an offline or an online approach. In this case, the system used was the Technomatrix process simulator. However, starting from a draft trajectory usually requires less development time than creating the trajectory from scratch. This is the basic idea of this paper. And the last but not the least, a very relevant component of the system is the robot. There are many collaborative robots such as the UR10 or the Fanuc CR35IA. However, some of them claim to be sensitive, like the Kuka Aiwa, which has been the robot used in TRAINMAN-MAGOS solution. This means that the robot provides extra sensory capabilities which can detect if the robot is hitting or touching something. This additional feature can be of high value when manipulating parts in mounting operations. Concerning project's development, the architecture diagram of TRAINMAN-MAGOS solution is composed by three main stages. The first one is training. The sensorized glove, currently using finger tracking and indoor localization system, produces an XML file with the readings of the sensors. The second stage is pre-processing. An offline simulation software consumes as input this XML file, adapts reference angles and units, and produces as output a CSV file that can be used directly as a set of trajectories and gripper instructions. And the third stage is execution. A set of gripper and sensitive collaborative robot move according to the CSV file. Thus, solution workflow starts by the performance of the dexterous operation by an operator wearing the Magos glove. Frequency of capture of the diverse sensors in the glove can be configured and was established in 10 Hz as a sufficient rate for providing fine trajectories. Since the gripper to be used has only 3 fingers, only data coming from 3 fingers from the Magos glove are considered. Thus, the data gathering from the glove provides data in X, Y, and Z axes and roll, pitch, and yaw angles from these 3 fingers' first joint angles. Due to the chosen gripper, pressure is applied at maximum in every case. While the glove registers information from the fingers, the tracker registers how the hand moves through the space by using a tracker device attached to the wrist and at least 2 base stations which define a workplace. This means that without the tracker, we would just have a stationary hand moving its fingers, while the tracker provides additional degrees of freedom to allow a proper register of the operator actions through the workplace. The offline simulation software takes the registered values from glove and tracker and concatenates these into a preliminary trajectory. Additionally, it adapts orientation and scales the read values into valid gripper instructions. The trajectory and gripper steps are manually refined in this virtual model by the robotic technician so that it can be finally implemented in real world afterwards. One of the main challenges is the synchronization of the orientation of both glove and robot to the center point. This means that both systems need to have a set of common reference points. In this case, it has been done, assigning 3 points in the space by using robotic pin calibration tools. Concerning the validation of the solution, a pre-industrial validation phase was developed, replicating a real industry use case as sample of its potential. An assembly of door class in automotive industry was chosen, mainly due to the fact that the product is fragile and it is an aspect element that cannot be damaged. Additionally, the assembly accuracy required is high and complex movements for placement and fixation are required. This use case was replicated in CTAC facilities and a set of car door, glass, and mechanical support to handle the door was prepared to support the tests. In order to prevent to damage the glass door, a glass-alike aluminum part was designed and manufactured to mirror shape and weight of the original glass. Additionally, the selected gripper was not fully prepared to grasp the glass-alike part with safety. Thus, a support was created allowing stable part gripping. Therefore, validation phase consisted on an iterative execution, so the solution was incrementally refined until obtaining a satisfactory result. We worked with more than 40 executions to reach a good final result. Once a good trajectory and gripping were obtained, a series of cycles were executed to check that this tuned trajectory was satisfactory in terms of long-term quality. 20 cycles of tests were launched, and as a result, the glass-like part was successfully placed in the 100% of the executions. Regarding cycle time, the tuned trajectory is equivalent or faster to the one performed by the operator during the training, so the achieved result can be complementary to the human task. Therefore, this validation proves that TRAINMAN-MAGOS solution is able to solve the demanding manipulation restrictions of a real manufacturing problem with a high resultant quality. About TRAINMAN-MAGOS advantages, the system has three main effects in the automation process. The first main effect is that the development time of robotic programs is decreased. The average time necessary to build a robot trajectory from scratch is radically reduced, providing a rough trajectory that can be further refined by a robotic technician. We have measured that this approach saves up to the 70% of the time that the usual procedure. The other effect is that commissioning time of the robotics application is also decreased. The time spent by the robotic technician making the final adjustment is reduced up to the 20%. This is due to the high quality of the drag trajectory provided by the hand movements recording. And the third effect is that the commission expenses are decreased. It's not rare to damage some of the involved products during the final adjustment of the trajectories. In the present use case, since the trajectories are of high quality when arriving to the manufacturing line, the probability of damaging parts is reduced up to the 20%. These improvement rates have been empirically calculated, taking into account staff experience in the field. Additionally, there are two other side effects of the usage of this solution. One effect is that expert knowledge, which is normally confined in the hands of the skilled operator, is saved by the company, being an important asset of the organization that should be managed and controlled. And the other effect is that from the ergonomics point of view, automating high dexterity operations usually means improving the operator's well-being by reducing repetitive, highly demanding tasks so the operator can use his or her time in more added value activities. So, we can conclude that TRAINMAN-MAGOS is a new solution to support robotic automation projects, based on the usage of a sensorized glove as a means to extract the dexterous know-how that is further translated into specific robotic instructions to be executed by a collaborative robot and a gripper. This way, manufacturing operations highly dependent of human manipulations could be totally or partially automated, being validated with the placement of the glass on a car door. TRAINMAN-MAGOS' main advantage is the robotic technician time saving, while creating and while installing the robotic solution in factory. It allows to obtain a draft robotic trajectory from the operator's hands by using specific tracking devices, instead of creating this trajectory from scratch. This makes it possible to save this important know-how and improve ergonomically the workplace. We strongly believe that this solution can unblock and boost the automation of high dexterity process on many manufacturing sectors, in which the classical robotic programming approaches are still the main option nowadays. The main future challenges to improve the solutions are making able to support as many robot and gripper brands as possible, including other sensors in the glove and the training phase, and validating the possibility of using two sets of robot and gripper at the same time so that operations using both hands can be successfully replicated. Finally, in the following video, you will see how the TRAINMAN-MAGOS solution works in order to support the automation of the glass assembly in a car door. As you can see, firstly, an operator using MAGOS glove picks the glass-alike part. Then, the operator performs the assembly of this part in the door. And, through the methodology explained before, the collaborative robot and gripper replicate this movement, saving thus the development programming time as we have previously explained. So, we have just come to the end of the presentation. We want to thank you for your attention and interest. If you find TRAINMAN-MAGOS interesting and you would like to get more information, please do not hesitate to contact us through the emails below. Thank you for the time.